this case study, a buck power supply development kit is used as a platform for an example buck converter. A bench supply provides bulk power to the kit at 9.2 volts with a 3 amp current limit. The buck supply regulates the output at 2.0 volts into a test load. The first task is to characterize the plant in system. A step input is supplied to the plant and the response is measured. The characterization data is imported into a PC tool that computes the system model. Next, the plant input is shaped and massaged until we are satisfied with the plant input and output. In this case study, we'll keep it simple and use an exponential plant input. Here is the plant input and plant output we are trying to achieve. These green lines here represent the desired plant input and plant output. Here is desired plant input, and here desired plant output. The blue line represents the expected plant input, and the red line represents the expected plant output. We will change the number of numerator and denominator coefficients until we are satisfied with the performance. For reference, a PID compensator is 3 numerator coefficients and no denominator coefficients, excluding the integrator. We will change the number of coefficients while observing the plant input and output. Our example compensator for this exercise contains 8 numerator coefficients plus 1 denominator coefficients plus an integrator. The design goal for this exercise is no overshoot and no oscillation, with a preference for increasing plant input and increasing plant output. Let's get started. First, let's look at standard PID performance, which is already shown in the system model. This is not very satisfactory. This is what we're trying to achieve, and this is how it's going to perform. We increase the number of numerator coefficients while observing the shape of the plant input and plant output. We can also see the numerator and denominator coefficients in these windows here. So this shows the numerator coefficients, and this will show the denominator coefficients. So I'll start increasing the number of numerator coefficients now. You can see the changes in the shape of the plant input and changes in the shape of the plant input. And you can also watch the numerical contributions of the coefficients in this window here. Continuing to about 23 coefficients. At 23 coefficients, the numerical contribution of the 23rd coefficient is less than 1 part in 1,000. We could keep going up to 50 or more coefficients to achieve even greater accuracy in achieving this desired plant input and desired plant output. But I think we'd be quite satisfied at 22 coefficients. So let's dial this back to 22. This compensator would implement the desired plant input that produces the desired plant output reasonably well. If we zoom in, have a look, it does a pretty good job. Now we ask the question, yes, we could do it, but do we really want to build a compensator that has 22 coefficients? The sampling frequency is 200 kilohertz, so we have 5 microseconds to sample the ADC, execute the compensator, and output the next PWM timer value. Can we do better? Yes. By adding 1 or more denominator coefficients, we can reduce the number of numerator coefficients and achieve similar performance. I'm going to dial this back to where we started. And then I'm going to add 1 denominator coefficient. That by itself made a huge improvement. Let's run this up to 4. Now you can see our overshoot is very, very small. After 4 numerator coefficients, adding more coefficients adds accuracy to the plant input and plant output. So let's increase this right on up to about 8 or 9. Now you may have noticed that as we pass through 3.1 and 4.1, those are both interesting possibilities. We'll come back to that later. Alright, so now looking here, we're at 9 and 1, and the numerical contribution of this ninth coefficient is relatively small. Let's dial it back to 8. We have 8 and 1. Zooming in to have a close look. The input looks pretty good. The output looks pretty good. A little bit of a dip right here. But all in all, not bad. So now we copy paste the numerator and denominator coefficients into the compensator code, build and run the project, and see how it performs. For each of these tests, we start by regulating steady state at 0.2 volts and then abruptly change the set point to 2.0 volts and then capture the action. This scope shot shows the system in operation. The top trace is the scope trigger. The next trace is the PWM timer pulses, basically the plant input. The next trace is the buck converter output voltage. And the bottom trace is a current probe point in the evaluation kit. Each pulse represents one 5 microsecond cycle. Initially, the PWMs are narrow. Here. The output voltage is steady at 0.2 volts. Here. And the system current is modest. Here. After the step, we can see the PWM pulses widen here. The output voltage rise and approach terminal value here. System current increases, then settles to a new higher value. See it come up, down, and settle in over here. Cursor lines were set to show 90% threshold for the set point step. Stepping from 0.2 volts to 2.0 volts is a change of 1.8 volts. 90% of that is 1.62 volts relative to the starting point of 0.2 volts, which is 1.82 volts absolute, right here. We see the output voltage crossing the threshold here. I would consider this performance to be quite acceptable, as determined by extremely low overshoot, a general rising plant input and rising plant output, meaning that the plant input is not being jerked around. For comparison, let's try the out-of-the-box demo compensators. These compensators all use 3 numerator and 1 denominator coefficients. The first compensator has a small overshoot, but quite a bit of oscillation and settling time. Note that the first PWM cycle is very wide, followed by narrowing PWM pulses, nearly zero width, and occasionally I have found a completely missing pulse here in this time slot. The system current clips here and oscillates. The output voltage also oscillates before settling. Number 2 is not stable. We wouldn't want to use this. Number 3 is stable, no oscillations, but very slow. Number 4 is identical to number 3. Number 5 is very, very slow, never achieving terminal voltage before the set point is returned to 0.2 volts. He starts, but he doesn't have enough time to get there. And then we set the set point back to 0.2 and it drifts back down. Now it's time to check the accuracy of the model. Data was measured in system for this compensator and compared to the performance predicted by the model. In the simulation, the model is allowed to settle in at the starting set point, then is abruptly stepped as was done in system with the proposed compensator. Here is the plant output measured in system compared to the system model predicted plant output. At first glance, it looks like there is very little difference between them. Let's look a little closer and check percent error. Here we see that the measured performance is within about 2% of the predicted performance, with the largest error near the beginning of the step, where the values are smallest. Left-hand side of the step is over here. The absolute values of, well, just referring to this picture over here, the model, the values are small at the beginning of the step, so the error tends to be a little larger. I think we can be happy with this result. Let's revisit the simpler compensator 3 and 1. We see that the absolute maximum is about 0.5%. Looking right here. If the shape of the plant input is acceptable, the shape of the plant output is acceptable, and the overshoot and oscillation is acceptable, then we could stop at 3 and 1 and say we're done. Let's zoom in and take a closer look. These green lines here represent the desired plant input and plant output. The blue line represents the expected plant input, and the red line represents the expected plant output. This is quite good, but let's continue on to 4 and 1. Now we can see the overshoot is about 0.03%. This is about 1 ADC count on a 12-bit ADC converter. Realistically, we won't see this error. We should be quite satisfied using this compensator. The point of continuing beyond 4 and 1 is only to demonstrate possibilities and capability, and accuracy in reproducing the intended plant input and plant output. By now you might be realizing that there are an infinite number of compensator solutions. If the plant input sequence is acceptable, the plant output sequence is acceptable, and the overshoot and oscillation is acceptable, then we're done. All we have to do then is pick a solution that we like. Almost sounds easy, doesn't it? Well, we had fun exploring compensators for this buck power supply and their impact upon plant input, plant output, overshoot, and oscillation. This concludes today's video. Thanks for watching.